A restless landscape in Northern California continues to challenge assumptions about volcanic quiet. Why does one peak, modest in elevation compared to its towering neighbors, hold the distinction of being the most active volcano in the state? What processes beneath its slopes keep it poised for change long after its last eruption faded from memory? And how does its past behavior reshape expectations for what might come next? These questions converge on Lassen Peak, a geological system whose activity is not defined by constant eruption, but by persistent signs of heat, pressure, and chemical transformation below the surface. Within Lassen Volcanic National Park, the terrain reveals a compressed version of the entire Cascade volcanic system. This region occupies the southern end of the broader Cascade Range, where volcanic processes taper but do not disappear. The landscape is not dominated by a single volcanic form. Instead, it presents a mosaic of features that reflect different eruption styles and magma compositions over time. Stratovolcanoes rise with layered deposits of lava and ash, shaped by repeated explosive and effusive events. Lava domes protrude as steep-sided accumulations of viscous magma that solidified near their vents. Shield volcanoes spread outward with gentle slopes formed by low-viscosity lava flows, while cinder cones punctuate the terrain as smaller, short-lived eruptions that built conical piles of volcanic fragments. This diversity is not incidental. It reflects the evolving chemistry of magma beneath the region and the shifting conditions that govern how that magma reaches the surface. Lassen Peak itself is not a stratovolcano in the classic sense, but a lava dome, composed primarily of dacitic magma. This composition, rich in silica, gives the magma a high viscosity. Instead of flowing easily across the landscape, it resists movement, trapping gases and building pressure. When it erupts, the result is often explosive, fragmenting rock into ash and pyroclastic material rather than producing long, fluid lava flows. The origin of Lassen Peak is inseparable from a much larger and older volcanic structure, Mount Tehama. This ancestral stratovolcano once dominated the region before undergoing a catastrophic collapse, likely driven by a combination of eruptive activity and structural instability. What remains today is not a single edifice, but a complex remnant system, within which Lassen Peak emerged as a younger feature. Its formation represents a later phase of volcanic activity, where magma exploited weaknesses in the crust left behind by the destruction of Mount Tehama. The eruption sequence between 1915 and 1921 provides a defining example of Lassen Peak's activity. This period began with relatively small steam-driven explosions, but escalated into more significant eruptive phases. Lava extrusion occurred as viscous dacite pushed upward, forming a dome that partially collapsed and generated pyroclastic flows. Ash plumes rose high into the atmosphere, dispersing fine material across large distances. The combination of lava emplacement and explosive fragmentation underscored the dual nature of dacitic systems, capable of both constructing and destroying landforms within short timeframes. Unlike basaltic volcanoes, where low-viscosity magma allows gases to escape gradually, dacitic magma traps volatiles such as water vapor and carbon dioxide. Pressure builds until it is released abruptly. This distinction explains why Lassen Peak's eruptions can appear intermittent yet still be considered highly active in geological terms. Activity is not measured solely by frequency, but by the persistence of underlying processes that maintain eruptive potential. Evidence of these processes is visible across the park's terrain. The ground in many areas appears young and barren, with sparse vegetation struggling to establish itself on fresh volcanic deposits. Boundaries between lava flows remain sharply defined, indicating relatively recent emplacement in geological time. These features contrast with older, more eroded landscapes elsewhere in the Cascade Range, highlighting the recency of Lassen's activity. From elevated viewpoints, another major volcanic presence comes into view, Mount Shasta. This stratovolcano, significantly larger and more symmetrical, represents a different expression of the same regional tectonic forces. Its snow-covered slopes and glacial features illustrate the interaction between volcanism and climate. Glaciers carve into volcanic rock, reshaping slopes and redistributing material downslope. However, these glaciers are retreating, a trend observed across much of the range. As ice diminishes, previously covered volcanic surfaces become exposed, altering erosion patterns and potentially influencing future volcanic hazards by changing how meltwater interacts with hot rock. One of the most striking manifestations of ongoing activity lies not in eruptive vents, but in hydrothermal systems. At Bumpass Hell, the surface is punctured by fumaroles, mud pots, and boiling pools. Steam rises continuously, carrying with it the unmistakable odour of hydrogen sulfide. The ground here is unstable, its crust thin and fragile above reservoirs of heated water and gas. Temperatures in these features can approach the boiling point, driven by heat from magma that remains at depth. The gases released at Bumpass Hell provide insight into subsurface conditions. Steam dominates, but carbon dioxide and hydrogen sulfide are also present, each playing a role in chemical reactions that alter surrounding rock. As these gases escape, they interact with groundwater and minerals, producing deposits of sulfur, pyrite, quartz, and opal. These minerals accumulate over time, coating surfaces in vivid colours ranging from bright yellow to milky white and rusty red tones. The hydrothermal system operates through a relatively straightforward mechanism, though its implications are complex. Groundwater percolates downward through fractures in the rock until it encounters heat from underlying magma. As the water heats, it becomes buoyant and rises back toward the surface, carrying dissolved minerals with it. Along the way, pressure decreases, causing gases to separate and minerals to settle out of solution. This continuous cycle of heating, circulation and deposition reshapes the subsurface environment and leaves visible traces at the surface. Auditory and tactile cues reinforce the sense of ongoing activity. Steam vents hiss and pulse, while the ground emits low rumbling sounds caused by boiling water and escaping gas. These are not signs of imminent eruption, but indicators of a system that remains thermally active. Such features distinguish Lassen Peak from dormant volcanoes where hydrothermal activity has largely ceased. The broader tectonic framework explains why this activity persists. The region sits above the Cascadia subduction zone, where the Juan de Fuca plate is being forced beneath the North American plate. This convergence drives a chain of processes that generate magma. As the oceanic plate descends, it carries water within its minerals. Increasing pressure and temperature cause this water to be released into the overlying mantle. The addition of water lowers the melting point of mantle rock, initiating partial melting. This process, known as metasomatism, alters the chemistry of the mantle and produces magma with varying compositions. Initially, the magma may be mafic, low in silica and relatively fluid. As it rises and interacts with the crust, it can evolve chemically, becoming more intermediate or felsic. This evolution involves processes such as fractional crystallization, assimilation of surrounding rock, and mixing with other magma bodies. By the time magma reaches shallow levels beneath Lassen Peak, it often has a dacitic composition, setting the stage for the type of eruptions observed in the early 20th century. The distinction between viscous and fluid magma is central to understanding the landscape. Fluid basaltic lava can travel long distances, forming extensive flows that gradually build shield volcanoes. In contrast, viscous dacitic lava accumulates near its source, creating steep domes that are prone to collapse. These collapses can generate pyroclastic flows, fast-moving currents of hot gas and volcanic debris that reshape the terrain in moments. Lassen Peak embodies this latter behavior. Its structure is inherently unstable compared to broader, gently sloping volcanoes. Even without eruption, gravitational forces can cause parts of the dome to break, particularly if internal pressure increases or if external factors such as earthquakes disturb the system. This instability contributes to its classification as highly active, even during periods of apparent quiet. Activity at Lassen is therefore not confined to dramatic eruptive events. It is expressed through a spectrum of processes, from subtle gas emissions to significant landslides and hydrothermal changes. Monitoring such a system requires attention to multiple indicators: ground deformation, temperature changes, gas composition, and seismic activity. Each provides a piece of the puzzle, revealing how magma and fluids move beneath the surface. The surrounding area amplifies the importance of these processes. The Southern Cascade Range marks a transitional zone where volcanic activity becomes less continuous but remains geologically significant. Lassen Peak stands out not because it erupts frequently, but because it exhibits a persistent level of unrest that reflects ongoing magma movement at depth. This combination of historical eruption, present hydrothermal activity, and tectonic setting defines its status as California's most active volcano. The classification of Lassen Peak as California's most active volcano becomes clearer when its behavior is evaluated over extended time scales rather than short observational windows. Activity here is not defined by constant eruption, but by continuity of internal processes that never fully subside. The geological system remains in a state of low-level unrest, sustained by magma residing beneath the surface and a hydrothermal network that continuously transfers heat and gas upward. This persistent energy flow distinguishes Lassen from other volcanic centres in the state that have been inactive for far longer intervals or lack comparable hydrothermal expression. The events of the early 20th century, particularly between 1915 and 1921, remain the most recent eruptive benchmark. Yet even after that eruptive phase concluded, the system did not return to complete dormancy. Instead, it transitioned into a state where magma remains present at depth, gradually cooling but still influencing groundwater circulation and gas release. The distinction between dormant and active becomes nuanced in this context. Lassen Peak does not fit neatly into either category. It occupies an intermediate state where eruptive intervals may be separated by decades or centuries, but the system itself remains dynamic. The rock composition plays a decisive role in sustaining this behavior. Dacite, the dominant material at Lassen Peak, is characterized by its high silica content, often exceeding 63% by weight. This composition increases viscosity, restricting magma flow and promoting the retention of dissolved volatiles. As pressure builds, even small changes in temperature or gas concentration can alter the stability of the magma body. This sensitivity ensures that the system remains responsive to internal and external triggers, whether they originate from tectonic stress, new magma intrusions, or changes in hydrothermal circulation. Over time, the accumulation and partial solidification of dacitic magma creates a structure that is both strong and fragile. The outer parts of the lava dome cool and harden, forming a rigid shell, while the interior may remain comparatively hot and partially molten. This contrast generates internal stress. If pressure increases beneath the dome, fractures can propagate through the structure, potentially leading to explosive fragmentation. Even in the absence of eruption, these stress patterns influence how heat and gases migrate toward the surface, sustaining fumaroles and hot springs across the area. The surrounding landscape provides further evidence of recent volcanic activity. Lava flows associated with Lassen Peak's eruptions remain clearly defined, their edges still sharply contrasting with older terrain. Vegetation cover is uneven, with some areas still barren due to the relatively young age of the deposits. Soil development is limited, reflecting insufficient time for weathering processes to break down volcanic rock into finer material. These visual indicators reinforce the fact that Lassen's most recent eruptive phase occurred within a time frame that remains geologically recent, even if it lies beyond living memory. Glacial features add another layer of complexity to the system. Although smaller than those found on Mount Shasta, glaciers and perennial snowfields once occupied higher elevations around Lassen Peak. These ice masses contributed to erosion, carving the landscape and redistributing volcanic debris downslope. However, glacial retreat has been ongoing, exposing previously ice-covered surfaces. As glaciers diminish, meltwater patterns shift, influencing how water infiltrates the subsurface. This, in turn, affects hydrothermal circulation, because groundwater availability directly impacts the intensity and distribution of hot springs and fumaroles. At Bumpass Hell, the interaction between water and magma is especially visible. The area functions as a natural laboratory where hydrothermal processes can be observed in real time. Fumaroles vent steam continuously, while mudpots churn with viscous mixtures of clay and boiling water. The boiling pools fluctuate in level and temperature, responding to subtle changes in subsurface pressure and water supply. Gas emissions remain steady, with hydrogen sulfide imparting a distinctive odour that signals ongoing chemical reactions beneath the surface. Mineral deposition at Bumpass Hell illustrates how these processes reshape the environment. As hot fluids rise, they carry dissolved elements that settle out when temperature and pressure decrease. Sulfur accumulates in bright yellow deposits, while iron-bearing minerals such as pyrite contribute metallic hues. Silica-rich solutions form quartz and opal, creating smooth, glossy surfaces around vents and channels. Over time, these deposits alter the composition and structure of the surrounding rock, a process known as hydrothermal alteration. This change can weaken rock strength, making the ground more susceptible to erosion and collapse. The hydrothermal system is not only a surface phenomenon, it extends deep into the crust, where fractures and porous zones allow water to circulate. Heat from underlying magma drives convection, with cooler water descending and hot water rising. This continuous cycle maintains the temperature gradients necessary for sustained activity. Any change in magma depth or temperature can influence this system, either intensifying or reducing surface manifestations. As such, hydrothermal activity serves as an indirect indicator of conditions within the deeper volcanic system. The tectonic environment remains the fundamental driver behind all of these processes. The Cascadia subduction zone continues to generate magma through the descent of the Juan de Fuca plate beneath the North American plate. This interaction is not uniform. Variations in subduction angle, plate movement and water content produce differences in magma generation along the arc. In the Southern Cascade Range, these variations contribute to the episodic nature of volcanic activity. Magma production may be slower compared to regions farther north, but it does not cease. Water plays a critical role in this process. As the oceanic plate subducts, it carries hydrated minerals into the mantle. Increasing temperature and pressure cause these minerals to release water, which lowers the melting point of the surrounding mantle rock. This leads to partial melting, generating magma that rises due to its lower density. Without water, the mantle would require significantly higher temperatures to melt, and volcanic activity in this region would be far less prevalent. As magma ascends, it undergoes a series of transformations. Initial mafic magma, relatively low in silica, may evolve into intermediate and eventually felsic compositions through fractional crystallization and interaction with continental crust. Each stage of this evolution changes the physical properties of the magma, including its viscosity, gas content, and eruptive style. By the time magma reaches shallow depths beneath Lassen Peak, it often exhibits dacitic characteristics, setting the stage for the type of eruptions observed in the historical record. The presence of multiple volcanic forms within Lassen Volcanic National Park reflects this diversity of magma types. Stratovolcano remnants, lava domes, shield volcanoes, and cinder cones coexist within a relatively compact area. Each represents a distinct eruptive environment, shaped by specific combinations of magma composition, gas content, and eruption dynamics. This diversity is a direct consequence of the evolving magmatic system beneath the region, where different magma batches can produce distinct surface features depending on their properties. Lassen Peak's position as a lava dome places it within the more explosive end of the volcanic spectrum. Dome formation involves the slow extrusion of viscous magma, which piles up near the vent rather than flowing far. Over time, this accumulation can become unstable, particularly if gas pressure builds within the dome. Collapse events can generate pyroclastic flows, while sudden pressure release can produce explosive eruptions that send ash high into the atmosphere. These hazards are less frequent than those associated with more active volcanoes, but their potential impact remains significant. Seismic activity provides another signal of ongoing processes. Although most earthquakes in the region are small, they reflect movement within the crust, often associated with magma intrusion or hydrothermal fluid migration. Monitoring these events helps identify changes in subsurface conditions, offering clues about whether magma is rising or gas pressure is increasing. Ground deformation, measured through satellite and ground-based instruments, can also reveal subtle swelling or subsidence associated with magma movement. The continuation of these processes underscores a central reality. Volcanic systems operate on timescales that far exceed human observation. Decades of apparent quiet do not indicate inactivity, but rather a slow accumulation of energy and change beneath the surface. Lassen Peak exemplifies this pattern, maintaining a level of activity that is subtle yet persistent, visible in every steam plume and mineral deposit across its slopes.